Welcome back to Calculus 3. I'm Dr. Jeff Grove. Today we're going to talk about Keplers laws. And before we get started, I want to recall some things to your memory. If you are calculating the area of a curve in polar coordinates, r is given as a function of theta, between some theta naught and theta final, the area is 1/2 the integral from theta naught to theta final of r squared d theta. Also, in polar coordinates, conic sections are given by r equals pe over 1 minus e cosine theta. Kepler had some nutty ideas about the solar system originally, dreaming of the planets being stuck on these nested polyhedra. But after spending a lot of time reviewing observations made by himself and also Tycho Brahe, working for Tycho Brahe as an astronomer, and after Tycho Brahe died, Kepler stole Tycho Brahe's notes. After many reams of computations, he came up with a much better idea about how the solar system works. Kepler's first law is that planets orbit the Sun in paths that are elliptical having the Sun at one focus. So if you place the Sun at the center of a coordinate system in the plane, the planet will move around it with actually the closest point of passage is at this part of the ellipse. That's called the perihelion. The farthest part is called the aphelion. If we have the axis of symmetry here, the center is here, and this is a focus. There will be another focus out here. Kepler's second law was that planets in their elliptical orbits will sweep out equal areas in equal times. It may be a shorter distance between points farther out in the orbit than points closer in, but if they sweep out the same areas, then it takes exactly the same amount of time. So in other words, planets will move more slowly when they're farther out in their orbits and faster when they're closer in. How did Kepler discover this? I mentioned his stolen notes from Tycho Brahe. Essentially what he did is we set up a kind of Riemann integral in the polar case, and instead of calculating the exact areas of these elliptical sectors, he approximated them by circular, getting a little too far here and a little not falling short a little bit here. And so he would approximate by circular sectors on each of these and get a pretty good estimation on the areas of these sectors for the ellipse. This is long before Newton and calculus. In fact, Kepler published these two laws in 1609. Kepler's third law, published in 1619, a decade later, says the square of an orbital period for a planet is proportional to the cube the mean distance. For thousands of years in Kepler's day, astronomers had used cycles and epicycles to try to predict the positions of the planets. They even had cycles on the epicycles after a while. In the age of Copernicus, before Kepler, Copernicus used only exact circular orbits. The circular orbits gave poorer predictions than the prior method using epicycles. Kepler's rules using ellipses finally gave better results than epicycles. In the preface to his 1619 publication, Kepler wrote, "I am writing a book for my contemporaries, or, it does not matter, for posterity. It may be that my book will wait 100 years for a reader. Has not God waited for 6,000 years for an observer?" You can see that Kepler knew he was onto something that was far better. It would revolutionize astronomy and replace the old theory of epicycles. But he wasn't sure of his work's reception. After all, he could look back and see what had happened to Galileo, or was happening to Galileo at that time. Astronomers had said before Kepler that objects up in the heavens must be perfect and untainted by sin, and therefore must go through a perfect path, of which there are only two, straight lines and perfect circles. So it was argued that since planets seem to return, they have to go on perfect circles. Of course, circles on circles was okay, but ellipses, those were bent and oblong and ugly. That couldn't be, but Kepler observed this to be the case, especially with regards to the planet Mars, which was a special study of his. In 1645, a French mathematician, librarian, and astronomer, Ismail Boulialdis, argued that the planets are propelled to move under some kind of force, and that force satisfies an inverse square law, predating Newton. Newton, of course, argued that objects not experiencing a force move in straight lines. Forces represent the time rate of change of momentum, and if the mass is constant, that's mass times the acceleration. Newton also argued that the force of gravity is proportional to the product of the masses of the two objects and inversely proportional to the square of the distance. But keep in mind, force is a vector quantity. So in what direction does this force go? I'm going to write this as minus g, where g is the gravitational constant of proportionality, the product of the two masses. Let's suppose, for the sake of the writing down of this formula, that object 1, mass 1, is at the center of some coordinate system, and mass 2 is not. Then there's a position vector, which we'll call r. Let's set little r to be the norm of big R, vector r. So little r is just a scalar quantity, whereas vector r is, of course, this vector. We can write this as follows. It's over r squared, but it still needs a direction because everything we've written down so far is scalar. The direction will be r over little r. This is a unit vector because we are normalizing the position vector. So this gives only a direction. The magnitude is determined by the coefficient. We can simplify this as follows. Minus g m1, m2 over the norm of the position vector squared times the vector u. Here we're assuming u is r over the norm of r. We're using a minus here because I'm thinking of the force of attraction for the smaller object, m2, towards the bigger object. If we negate this vector u, the force will be going in. It's possible to show that an object moving under Newton's inverse square law for gravity will have zero torsion, and hence the path will lie on a plane. So we're going to make the following assumption. We're going to suppose that the vector r, the position vector, is in a plane. We'll write that as r times cosine theta sine theta, like this, just like we have in the recent past. But we're going to introduce a new notation. We're going to set u to be the unit vector cosine theta sine theta. Keep in mind that if this position vector really is the position of a planet orbiting the sun, with the sun at the origin of a coordinate system, then both little r and theta are functions of time. The velocity vector, if the position vector is given like this, where we have r, u now, the velocity vector will be the derivative with respect to time of that position vector. That's going to be r dot u plus r u dot. Now I want to investigate this u dot, the derivative of u with respect to time. U dot is going to be calculated using the chain rule for each of the coordinates, with the cosine function with the theta function inside. That's going to give us minus theta dot sine theta. The derivative of cosine is minus sine, leave the inside alone, and then multiply by the derivative of the inside. Dots, of course, representing derivatives with respect to time. The derivative of the second coordinate is theta dot cosine theta. All of this simplifies as theta dot times minus sine theta cosine theta. I want to think about this vector a little bit compared to the vector u. If we dot u with the vector minus sine comma cosine, we end up with negative sine cosine plus sine cosine, which is 0, which means this vector is orthogonal to u. I'm going to introduce another notation. We're going to set u perp equal to the vector minus sine theta cosine theta. So notice that the derivative of u is theta dot times u perp. Also, the derivative of r, the velocity vector, is r dot u plus r theta dot u perp, according to this equation. You can see that the first term in the velocity vector points in the direction of the radius vector and is proportional to the rate of change of the radius. This is the radial component of velocity, whereas the other part, the second term, is orthogonal to that. That's kind of the rotational part of the velocity. Now, how about that acceleration vector? We have to take the derivative with respect to time of the velocity vector. To do that, we're going to need to know the derivative of u perp. So let's figure that out. U perp dot. If u perp really is minus sine theta cosine theta, we're going to get minus theta dot cosine theta minus theta dot sine theta. If we factor out the minus theta dot, we end up with cosine theta sine theta but that's the vector u. So we get minus theta dot times the vector u. So calculating the derivative, we'll have, using the product rule, r dot dot times u plus r dot, remember the derivative of u is theta dot u perp, and then we have a triple product rule next. That's going to be plus r dot theta dot u perp again, plus r theta dot dot u perp, and then the derivative of u perp, that's going to be minus r. We get two factors of theta dot now, so we get a theta dot squared times u. Now, according to Newton's force law, the acceleration of that object number 2 times the mass is equal to the force, which is given by this exact equation times m. We'll have 2 r dot theta dot u perp plus r theta dot dot u perp minus r theta dot squared u. And according to Newton's inverse square law, that's minus g m1 m2 divided by r squared times u. You can see that the m2 will cancel off, and we have an equation involving both the vector u and the vector u perp. This notation will really pay off if we notice that, first of all, u dot u is 1 because u is a unit vector, and when you dot a vector with itself, you end up with the norm squared. U dot u perp is 0 because these are orthogonal, and u perp dot u perp is 1 because u perp is also a unit vector. Now, if we dot everything in sight in this equation with u, we'll have r dot dot because u dot u is 1. When we dot u on the second term, we get 0, so that will drop, and the third term also drops. What's left is minus r theta dot squared times 1 equals, dotting with respect to u on the right-hand side gives us minus gm1 divided by r squared times 1, since u dot u is 1. This gives us one differential equation in two unknowns. The two unknowns are the function r and the function theta. We can get another equation by dotting the same equation by u perp instead. When we dot the first term with u perp, we get 0. On the second term, we get 2 r dot theta dot times 1. And then we get plus r theta dot dot, and then 0, and then equals. When we dot with respect to u perp on the right-hand side, we get 0. This gives us two equations in two unknowns. They are differential equations, and that makes them a little bit tricky to solve. Let's play with the second equation for a little while. Let's divide everything in sight by r theta dot. Right-hand side 2, but that just gives you 0. On the left-hand side, you'll get 2 r dot over r plus theta dot dot over theta dot equals 0. Thinking about these two terms, isn't this the derivative of something? Do you remember that anytime we integrate f prime of x over f of x, we get log absolute value of f of x plus a constant? These are both in the form f prime over f. We have the derivative on the top of what is on the bottom. The second order derivative of theta is the derivative of the first order derivative. Integrating, we get 2 log absolute value of r. We'll assume r is positive, so the absolute values are superfluous. Plus the log of theta dot equals some constant of integration. We can now use a property of logs to bring the square up, and then combine the two logs as the log of r squared theta dot equals some constant of integration, and exponentiating, we'll have r squared theta dot equals some other constant of integration. I'm going to express that constant as 2a. I'll multiply by 1/2 to get rid of the 2 here. And we'll have a is 1/2 r squared d theta dt. We'll multiply both sides by dt, putting the dt onto the left, and then integrate both sides. On the left-hand side, we'll integrate from t0 to t final, and on the right-hand side, we'll suppose that at t0, theta will be at some theta naught, and at t final, theta will be at some theta final. What you get here is a times the change in t. Since a is constant on the left-hand side, you just get the constant a times the length of the interval, which is t final minus t naught. That's going to be equal to the integral of 1/2 r squared d theta from theta naught to theta final. The very first formula that I wrote down on the board in this lecture was that this represents the area being swept out by some curve. So this is the area of the region swept out by a planet moving under Newton's inverse square law. And according to this principle, that area is equal to a constant times the change in time. It's proportional to how much time has elapsed. It has nothing to do with where it is in the orbit. So when you're far out in the orbit, a certain amount of time elapses, you're going to sweep out a certain area. When you're close in on the orbit and moving fast, a certain amount of time elapses, you're going to sweep out that area. It doesn't matter how far and how slow or how close and how fast you are in the orbit, equal areas for equal times. This proves that Newton's law, inverse square law of gravity, his universal law of gravitation, implies as a consequence Kepler's second law. What is the significance of this constant A? A is the rate at which area is being swept out. This must be area per unit time, because when you multiply by an interval of time, you end up with area. So A is the rate area is swept out in units of, say, square kilometers per hour or square kilometers per day, whatever unit of time and area you wish to work with. Solution of Newton's other law, which was r dot dot minus r theta dot squared equals minus g m1 over r squared, will require a little more finagling. We're going to have to do a couple different maneuvers to simplify this and make it easy to solve. The first maneuver we're going to make is kind of a genius idea due to Newton himself. It's to replace r with another variable u, where they're kind of inversely related to each other. This is kind of flipping the universe, where r is 0, u will be infinity, and where r goes to infinity, u goes to 0. So note that r is 1 over u, and that means r dot is going to be negative 1 over u squared u dot. The derivative of 1 over x is negative 1 over x squared. By the chain rule, we have to multiply by u dot. then? What is our dot dot? That's going to be 2 over u cubed. We get another factor of u dot by the chain rule, and then minus 1 over u squared u dot dot. We still have this theta dot to deal with, but we have the formula 1/2 r squared theta dot is equal to the rate of area being swept out, A. That means then that theta dot is 2a divided by r squared, or 2a times u squared, with this change of variable. How does that affect the equation? Well, we'll have 2 over u cubed u dot squared minus 1 over u squared u dot dot minus 1 over u. That's going to be 4a squared u to the 4th. And that's going to be equal to minus gm1 times u squared. It's at this point there's a second maneuver that needs to be made. It stands to reason that theta changes with time, or time changes with theta. There's a direct correlation between them. As time goes by, the theta will increase in the orbit. We can try to change all of these derivatives with respect to time into derivatives with respect to theta in the following way. du dt is du d theta dt. Let's write du d theta by u prime, Newton's way of denoting derivatives with respect to a spatial variable used a prime. We have here a theta dot, but theta dot is 2a u squared. So we get 2a u squared u prime in place of du dt, which is u dot. What about u dot dot, which is needed in our equation? That should be the derivative with respect to time of u dot, which we know to be this. This is going to be d theta dt times the derivative with respect to theta of u dot, which will replace by 2a u squared u prime. Theta dot here is again replaced by 2a u squared. We'll have another 2a, but we'll take the derivative with respect to theta of everything that's left. That gives us 2u u prime squared plus u squared u prime prime. We can now make substitutions into this equation. You can see that we will have 2 over u cubed. U dot gets replaced by 2a u squared u prime, but that gets squared, minus 1 over u squared times u dot dot. That's going to be 4a squared times u squared times 2u u prime squared plus u squared u prime prime. Then we have minus 1 over u 4a squared u to the 4th, and that still equals minus gm1 u squared. You can see that we have a lot of things that we can simplify here. 2a gets squared, so we'll have a 4a squared. We have a 4a squared here and a 4a squared here. Let's divide that off to the other side. That takes this away, and this away. What else can we ditch? Well, here we have a u squared squared. That's u to the 4th. That's divided by a u cubed. So if we put a u in front we can cancel that off. We'll have 2u times u prime squared. This u squared will cancel this u squared. And then what's left over? Here we have 2u u prime squared. We'll have a minus 2u u prime squared. So this whole term will cancel this whole term. Now, where are we? We still have this minus u squared u double prime. We have minus u squared u double prime. We still have this minus u cubed equals minus gm1u squared over 4a squared, all of this being a constant. If we multiply both sides by -1, we can turn all terms into positives, and we can divide by u squared, and we get u prime prime plus u equals the constant gm1 over 4a squared. These sorts of equations are very easy to solve using elementary theory from our differential equations courses. The general solution will have two constants of integration because we have to undo two derivatives. It will be of the form u equals the constant k plus a constant of integration c1 times the cosine of theta minus some theta naught being the second constant of integration. It follows then that with the k equals g m1 over 4a squared, that if u is 1 over r, then r is 1 over this constant k, I'll write that as k for simplicity, plus c1 cosine of theta minus theta naught. If we multiply top and bottom by 1 over k, we'll get a constant, which we'll denote by PE, it's the reciprocal, over 1, I'll write this as minus some constant of integration, which I'll call C2 cosine of theta minus theta naught. And C2 is the eccentricity E. This is clearly identifiable as the second thing I wrote on the board today as a conic section. This verifies that Newton's universal law of gravitation, his inverse square law, implies Kepler's first law. Planetary motions must follow ellipses. There are only three kinds of conic sections that concern us: ellipses, parabolas, and hyperbolas. If an object is moving lower than escape velocity, it must move in kind of an elliptical shape. If it reaches escape velocity, it will follow a parabola. And if it is moving at faster than escape velocity, it will follow a hyperbola. The effect of the theta naught here is a simple rotation of the conic. We can rotate the conic to any position we need for our coordinate system. Remember that A was the rate at which area is swept out. If the area of the entire ellipse is pi AB, where A is the length of the semi-major axis and B is the length of the semi-minor axis, and if T, capital T, is the period, then A will be pi AB divided by T. We can plug this into the formula that we have here, obtaining G m1 over 4 pi squared a squared b squared with a t squared on top equals 1 over p e. E is c divided by a. The eccentricity is the distance from the center to a focus divided by the length of the semi-major axis. It follows then that if we multiply both sides by this constant p and multiply both sides by a squared b squared, we'll have the square of the period times a constant equaling something involving just a, b, and c. For an ellipse, c squared is a squared minus b squared. So we can make certain substitutions here. Evaluating the formula r equals pe over 1 minus e cosine theta minus theta naught, we can set theta naught equal to 0 if we wish, putting the ellipse into a nice standard position. If we evaluate the function at theta equals 0, we get the If we evaluate at theta equals 0, we'll be subtracting the maximum amount, and we will be at aphelion. If this distance from the focus to the center is c, and the distance from the center to a vertex is a, then a plus c will be pe divided by 1 minus e. If we then evaluate at theta equals pi, we'll have a minus c. These two formulas imply that p is equal to a squared minus c squared over c. A squared minus c squared is b squared. We can make that substitution here. We have then b squared over c times gm1 over 4 pi squared p squared equals a squared b squared over, well, a cubed b squared over c. The c will cancel, the b squared will cancel, and we'll be left with the square of the orbital period is proportional to the cube of the length of the semi-major axis, which is the mean distance. This proves that Newton's universal law of gravitation implies Kepler's third law as well. So this one principle, Newton's universal law of gravitation, together with his law of force, implies all three of Kepler's laws. Kepler's laws were purely descriptive, leaving gravity a little bit more of a mystery. Newton's law describes gravity as an inverse square force law. This is better mechanically, but as you can see, it does take a little finagling to work out.